Yes, thank you for being part of lecture number 10, Null Spaces and Eigenvalues. Okay, we're going to talk about subspaces to start off with so that we can get a better definition of these. So when we talk about subspace, this is what it's talking about. Here's a subspace, that's what that S stands for, the elements of C, any C times the vector V1 is in this subspace. Subspace is a linear vector space. So it's all linear. So we can say that we can multiply it by a large number or by a fraction, so we can make this vector larger, expand it, or make it shrink, or make it negative. Okay, as an example, a plane in 3 dimensions. So this is a plane, okay, and this is a linear vector space, a subspace. That's what we're looking at. This one is 3. The 3 represents the 3 dimensions, x, y, z. Okay, for V1 and V2, elements of the what? Of the subspace. And that is for all C, all values of multiples of C that are in the real numbers system. Okay, so we can see the multiplication works and keeps it within the linear vector space. So now when we add vectors together, they also stay within the vector space. So we can say that the addition and multiplication of vectors, they call it closed. Okay, so it continues, okay, closed under addition and multiplication means it works when adding and multiplying these vectors, that we stay within the subspace. We did not go outside of the subspace. A null space is the space defined by the A matrix and the equation AX equals 0. Or we could look at it another way. Let A be an M by N matrix. It doesn't have to be a square matrix. The null space is the set of solutions. This is the key. The set of solutions, that's what we're going to be trying to hunt down. The set of solutions of X to the homogeneous solution. To the homogeneous system. Now, when we studied differential equations, we had homogeneous and particular solutions, and we added them up to get our total solution. The nullity is the dimension of the null space vector. So it depends on what is the dimension. And this is 3-dimensional here. The other one, this one is 2-dimensional. Okay, so if we look at this particular one, the null space vector defines the null space where they are equal to 0. Okay, which we just said here. This means that the rank of A plus the nullity of A equals the dimension A. Okay, so this is a 2 by 2. Okay, so we're going to multiply. So we're going to use row reduction. So we're going to multiply row 1 by row 2. Now, if you look here closely, you can see that row 2 is nothing but a 2 times row 1. So we've talked about before that one of the rules are if they're multiples of each other, as it's here, it's still the same vector. It's just a different length. Okay, so then they will equal 0. Okay, so when we multiply row 1 by 2 and subtract, then we could get 0, 0. For a null space to exist, A must have some linearly dependent rows. Okay, so these are, and as you can see, what is this? These are linearly dependent. They're the same exact ones, just multiplied by 2. Where the determinant of A equals what? 0. If you multiply this, 2 times 2 is 4. 4 times 1 is 4. 4 minus 4 equals 0, just as we had noticed. Okay, let's look at this first practice problem. We're going to be looking at two different vectors, two different matrices. We're going to be looking at matrix A, and we're going to be looking at matrix B. Okay, so let's take a look at this one. Is the easier one, so let's look at the B first. With B, you can see that row 2 is nothing but 2 times row 1 and a minus sign. And as you can see here, row 3 is just 3 times row 1. So you should expect to find what? That this is going to equal 0, because these are just multiples of each other, as we mentioned. So if we multiply 2 times R1 okay, and then we add that to row 2, we get 0, 0, 0. Now if we multiply row 1 by 3 and then subtract it from row 3, we get 0, 0, 0. Okay, so what we have left is these are trivial. These don't mean anything. These give us no information. This is the only row that gives us any information. So this tells us that x, 2x plus y plus z equals 0. Okay, so now let's go over to this one, and we'll finish this one up on this next page. Okay, so right here, what we have is that this is not multiples, so we have to work a little harder. But we need to get some zeros in here. Okay, so if we take row 1 and multiply it times 2, and then add it to row 2, we get 0, 1, minus 3. If we then take row 1 and row 2, add them together, okay, this will go to 0, this will be 1, and this will be minus 1. So now we have what? 2 zeros, and we have 1s. Okay, so we have these 2 zeros, which are very important for us. Okay, so the equations that we have here says that this is x minus z equals 0. Okay, so that means that x equals z. And we have for this set of equations, okay, we have y minus 3z equals 0. So y equals 3z. So our null vector, okay, we can pick any value for z, any value. Okay, so we just pick 1 for z, as this example. Then if z equals 1, then x equals 1. And then y equals 3 times 1. Okay, so we have here 1, 3, 1. So this is the null vector for matrix A. So now we want to go back to matrix B, and we're going to find it. Okay, we're going to continue there. We have 2x plus y plus z equals 0. So with this equation, we can see that z equals a minus 2x minus y. So if we let x equal 1 and y equal 1, then we know that what? Z equals a minus 3. So then that tells us we have 2 null vectors for this equation. So we have for v1, we have 1, 1, minus 3. So now we're going to let, like I said, we can let it equal anything. So we're going to let x stay at 1, but we're going to change y to a minus 1. Okay, so x is 1, y is a minus 1. Then we find out what z is. Okay, so here is z is equal to a minus 1. So here we have 2 null vectors. Okay, definition of eigenvalues and vectors. As you can see here, we have x1, and then we have t at x1, a function that's using t, that's using x1, this vector, okay? This function is using this vector. And we have x2, and we have x3, and each one of them these are, if you notice, you have an angle here for each of these. So we have an angle here for x1, for the tx. We have an angle here, the same thing. We have an angle here also for T3. Okay, now when we use our eigenvalues and our eigenvectors, we are now wanting to be able to say, okay, what value of lambda, what constant can be multiplied times of a new vector to give us the same answer, okay, to give us the same function. So that's what we're going to try to do. Let A be a square matrix, an n by n matrix. A scalar lambda is called an eigenvalue of A if there is a non-zero vector x such that A of x equals lambda at x. So some number times x is going to be equivalent to ax. Such a vector is called eigenvector of A corresponding to lambda. Okay, note, if lambda is an eigenvalue of A and x is an eigenvector belonging to lambda and non-zero multiple of x will be an eigenvector. So we're not using any multiple that's non-zero. We're not using 0. Okay, so assume that ax equals lambda x. Okay, so we want to rearrange this equation here. Okay, so we're just taking a, just a constant outside from the x. We can take it all the way out. So now we're going to compare this to lambda x, and so we get lambda times ax. And so since we have a times ax, that's this constant, times that vector, as you can see, we have our eigenvectors, eigenvalues and eigenvectors. Okay, lambda 1, lambda 2, and they are supposed to represent, to give you the same value as what? T sub v at 2. Eigenvector, a vector that only scales under transformation of A. The direction is unchanged. Only the magnitude changes. Very important. Okay, so as you can look here, you can see that we have T. Okay, we have A of x, and here's A of x, and we have x and y. Okay, what vector, we want a vector such that we will have this vector, A times x, this vector will equal lambda times the eigenvector. This is the eigenvalue times the eigenvector. Lambda is called the eigenvalue. Eigenvector, a vector that only scales under transformation. Remember, it doesn't change direction. Okay, we have here x1, and if we plug this in, let's use for 1, let's plug in 1 for here and 1 for here. Okay, and if we plug in the ones, we get 3, 0. So if you look over here, you have x1, and this should be 1, 1. And so where is t? x1. This one is here at 3, 0. See that? Okay. Okay, we want the value such that x2 equals 1, 3. Okay, where's x2? x2 is 1 going up 3. When you multiply it out, when you put it in the equations, you get minus 1, 4. So notice we're using t, transformation of v. We're using a times v, lambda times v. Lambda is called the eigenvalue. Okay, so for our third one, we're going to use -1 minus 1/2. So this is a -1 minus 1/2, and this is going to give us the answer of a minus 4, 1. Okay, finding the eigenvalues. Okay, if A times the vector equals lambda times that vector times the eigenvector, then we know that we can take everything to one side, and then we'll have to multiply so that we can add these and subtract them. They have to be of the same dimensions. So we use the identity matrix times lambda. Okay, so that'll be a minus the lambda times the identity matrix. All of these are multiplied times what? The eigenvector. Okay, proof starts. We find a way to write lambda or eigenvalue times the eigenvector. Okay, so we have here our eigenvalue times our eigenvector, and there we have it, breaking it down a little more detail, eigenvalue with x and y. Then we want to multiply it times the identity matrix, which is 1, which doesn't change anything. And as you can see, only the diagonals, everything else is 0. Then we multiplied lambda times this vector, we get lambda, lambda. So now what we would like to do is, we said already that this vector times this matrix, this is the matrix A times the value times the eigenvector. So we're going to say it's equal to the lambda times this vector, same vector. So what we need to do is be able to take everything on one side, and so what we do is the lambda, it's minus lambda, 5 minus lambda, and 2 minus lambda. The other ones stay the same. The minus 2 doesn't change. Okay, for the solution, for eigenvector cannot equal 0, the matrix of A minus lambda, the identity matrix, must be linearly dependent. Therefore, let the determinant of A minus lambda I equal 0. So we have here let's multiply this out. We set this equal to 0. This is 5 minus lambda times 2 minus lambda minus 2 minus 2 lambda equals 6, 7 lambda, lambda squared. This is called the characteristic equation. From this equation, we can now solve for lambda 1 and lambda 2. So lambda 1 equals 1 and lambda 2 equals 6. Okay, we will do one more example for us so that we can hopefully make sure that we understand it a little better. Okay, so find the eigenvalue of the transformation matrix. Okay, so we have A, and we're going to say A minus the identity matrix minus lambda. Okay, so we have here 2 minus lambda for the diagonal. Everything else stays the same. The 1 minus lambda and 2 minus lambda. And so the easiest one that we will be able to multiply everything times is this one, is this second row. Okay, we got 2 zeros in it, so that means that all we have to do is multiply times a negative, this negative 1 minus lambda. So we have negative 1 minus lambda. We're using 2 minus lambda, and we're using 1, and we're using 1, and we're using 2 minus lambda. And so that gives us a minus times the quantity 1 minus lambda. And we have here what? 2 minus lambda squared minus 1. We multiply this out. We get a minus 1 times 1 plus lambda and lambda squared plus 4 lambda plus 3. And that breaks down to, we now have what? A 1, a 3, and a minus 1 for our eigenvalues. So now, hopefully you can do this. And so we are giving you this to do as your practice problem. All right, enjoy, and we hope that you play it back as much as you need so that you might be able to understand what we were doing. Thank you, and have a nice day.